it means to be human.
Where did we come from? Oh no!
My name is Stepphen Hawkings, and I believe that anyone can answer big questions for themselves. So with the help of 3 ordinary people and a team of experts,
we have come to understand our origins, and this is new.
We are going on the ultimate voyage.
Wow, that's impressive.
A quest to answer the greatest mysteries of the universe. Using the power of the human mind.
Wow! It must have been so exciting to see that for the very first time.
Because anyone can think like a genius.
Genius by Stepphen Hawking was made possible in part by contributions to your PBS station from viewers like you. Thank you.
What are we?
What are we?
Have you ever wondered what you really are? Have you ever stopped to think how you got here? A complex biological creature living on a ball of rock spinning through space. If so, you are in good company. What are we is a question that has been asked for thousands of years, contemplated by some of the greatest minds who ever lived. But even today, far too few people know the answer. So let's see if we can put that right. I have asked 3 curious minds to join me on a journey of discovery. A series of fun challenges awaits them. They will be given tools and equipment. Can they follow the greatest thinkers in history and grasp what we really are? The first step to finding out is to ask, what is life itself?
What is life? That's a difficult question to answer.
What is life? It's kind of seems like a very simple question.
Something which is able to, which is born and can reproduce itself.
Receiving energy, giving energy.
Reproducing and reacting to the world around you.
That's a really tricky question to answer.
This machine illustrates the first key principle behind what you are. It has lots of moving parts that trigger each other in a chain reaction. It's designed to reveal something that you may find disturbing. Will my volunteers get the point of the machine?
Interesting.
Yeah.
Okay.
First, they had to find out how to start it.
I wonder what happens over here, though. Look at this arm. It's not supposed to be like a God thing, you know, because it's an arm out of the clouds or whatever.
I think you're probably right. It's beginning up there. Should we give it a go and see if it'll work?
Yeah, that's what's going on over there.
I think it starts up here, right? Give me a countdown, guys.
Okay, 5, 4, 3, 2, 1. Okay. Whoa.
To the top of this. Yes. Keep going.
Nice.
Okay.
I love that.
Oh, I think it's got stuck.
The machine works by transferring an impulse from one place to another, sustained by the input of energy. There are lots of different moving parts, each following the laws of physics, and together they keep the impulse moving.
Is it going to be enough? Yeah.
Stepphen Hawking's Shield of Life.
So what has this got to do with us?
what do you think? Reset it in order?
Let's try and reset it, and maybe they'll help us figure out one thing always leads to another. So one process has to happen before another process happens. Like certain circumstances have to occur before something can move forward.
It helped to show me that everything has a cause and effect. It reminded me all about chain reactions.
So I guess you need a cause and effect, and everything has to build up and up and up.
Should we give it a go?
Let's give it a go.
I think it might have broken.
No,
Okay.
Whoa.
Oh, go! Nice. Did we reset it correctly?
It was a really powerful demonstration of how all those processes work together.
Oh, yes!
You've got all these different things that create one result.
It's gone premature.
That's okay, that's okay.
My machine is actually a very simple version of what is going on inside your body. This is what you look like on a microscopic scale, and it really is quite incredible. Where my machine features dominoes and pool balls, your body has molecules, chains of atoms of carbon, oxygen, hydrogen, and other elements. You are made of billions of tiny machines, all triggering each other. You are a giant chain reaction machine. Discovering this has taken centuries of work by scientists. It all began by looking at a drop of water.
People had always assumed that what they could see with their own eyes was the limit of the physical world. But all that absolutely fundamentally changed in the middle of the 17th century, when a Dutchman called Anthony van Leeuwenhoek made one of the greatest scientific discoveries of all time, and yet he himself was a cloth merchant, a draper. It was his interest in microscopy, microscopes, that he was using to examine the quality of cloth, that he then, with his innate curiosity, kind of applied to the world around him, that literally opened up a whole new world of science. This is a replica of his own handmade microscope. And this, believe it or not, it might not look like very much, but this was the most powerful microscope around at that time. Sandwiched between these two sheets of metal is a tiny glass sphere. And whatever you had attached to this spike here, you could see magnified just over 200 times. He took a droplet of water, and when you held it up to your eye, like this, he saw what no one had ever imagined. This whole new world. The water droplet was literally teeming with life. He described them as little animals. To us, we now know that they are microorganisms. It must have been so exciting to see that for the very first time. He looked at all sorts of things using his microscopes. He looked at himself. He looked at skin, and he looked at blood. We are all fundamentally made of similar things.
The idea that we might be made up of invisibly tiny components was something of a shock. After all, nobody likes to think of themselves as a machine. Not even me. But let's go back to the contraption, because it has another feature. It can be made to run round and round in a loop. To do that, we need one more part. This rather attractive plastic figure joins the end of the machine back to the beginning. Now the challenge is to keep it going.
We would have to put in enough energy and be quick enough to reset the pieces before they came round again.
Make it run in a loop? I can try. That's what I can do.
Making a chain reaction machine run in a loop should help the team understand what we are.
If we get 5 cycles, I'll buy the drinks.
Yes!
Okay, let's do this.
3, 3, 3, 2, 2, 2, 1, 1, 1. Go!
Now the machine is also like the circle of life itself. A cycle where the impulse is passed from one living organism to the next.
I need help over here, help over here, help over here.
As long as there is enough energy, and there is no great disaster, this impulse will keep going.
And Hawkins reset.
All of a sudden felt like a lot of pressure. I wanted it to succeed, and I wanted it to, I wanted it to run.
I'm quite OCD about these things, so I really wanted it to work.
Oh God, here we go, next one.
At the most fundamental level, life is not a thing, it is a process.
How are we doing?
We're doing well.
A process that can last indefinitely, as long as there is no disaster. A process that depends on tiny machines, each one triggering the next.
The minute something is wrong, even by, say, a quarter of an inch, it's not happening.
It was a challenge. It was a physical challenge because as you did it more and more, you had to run around more and you were getting more tired.
Okay, the balls.
But sadly, in the real world, mistakes are eventually made.
Having a bit of trouble here.
Oh God, it's coming again.
And if there are enough of them, the machine stops.
Well done.
So close. Sorry, guys.
You did a good job.
We got about 4 or 5 goes round, so it was a pretty good go. What it taught me about life was that we have all these random processes going on inside us, but we need all of them, and we need all of them to work in order and build upon one another to make the final result, which is us.
I'm made of little machines like that, but where did those machines come from? How were they created in my body?
So now they know life is a process inside a wonderful machine. My volunteers are asking the next question. How did this biological machinery come about? This is the next step on our journey to discover what we are. Time for the second challenge. These blue and yellow pieces might not look like much, but they hold a secret. Will my volunteers work out what it is?
What are they?
Are they made out of foam or plastic?
Blue and yellow pentagons.
I was really confused. I wasn't sure what they were.
First thing I wanted to do was touch them. Immediately I was just really excited.
Okay, they're magnets.
Okay, so they stick together.
Different colours. We've got some propelling each other.
It looks like we can sort of put the blue ones together into sort of domes. As soon as we got a couple together, we realised that there were some laws of attraction between the different blocks.
I wonder how big we can make one.
You're far too fast at that.
Yeah, you're
You left me way behind.
It's kind of cool though. It looks like a virus.
Making little discoveries about, ooh, this works better this way, and this works better this way. And, ooh, you can make a ball. Amazing, you can make a ball.
So what do these magnets represent?
Can we do a mixed sphere? I don't know.
See, I've gotten like a little half and half kind of thing here, but it's just not having
So
it.
I guess we can get sort of planar, regular sort of chains with the mix.
How did you do that?
Just end to end. Blue one the sort of right way up and the yellow one the other way up.
I see.
The ones of similar colour were very easy to link together in the same orientation, whereas between colours that wasn't the case.
All right, so we can get a little bit of bonding and binding.
It kind of reminded me of molecules, I guess.
These clusters of magnets are indeed like molecules. And the individual magnets, like atoms of different elements. Things like carbon, oxygen, or hydrogen. They have positive and negative charges, attracting or repelling each other. Each different combination creates a different molecule, and many combinations are possible.
It's interesting because obviously each one, right, has different properties. So these are clearly much stronger. These ones, they just fall apart.
We quickly discovered that we could get 3D structures with ones of similar colour, but only kind of plain and flat structures with mixtures of colours. but we saw that we could, within those restrictions, make a myriad of different patterns, of fantastic combinations.
The tiny machines inside you are built of just a few kinds of molecules. One of the most important is amino acids, often called the building blocks of life. By the early 19th century, scientists knew about these molecules, but had no idea how they first formed. To find out, they had to look more than 4 billion years back in time, before the beginning of life on Earth.
So a big question in the sort of early study of the origin of life on Earth was, where do these basic building blocks come from? Do they just appear out of the blue? A remarkable experiment was started in the 1950s by Stanley Miller, who was a PhD student at the University of Chicago, along with his advisor Harold Urey, built a system composed of a glass globe that was sort of mimicking the atmosphere on early Earth. A lower ocean that was a globe that contained water that was heated, and water vapor rises through a glass tube into the atmosphere. In this upper atmosphere, he had 3 gases in addition to water vapor. He had ammonia, methane, and hydrogen. And these are gases that were thought at the time to be in high abundance in the early Earth atmosphere. And there's no oxygen present. And in this flask, he had an electrical coil that provided energy into the system. You could imagine that as lightning. And then he turned the electricity on in this closed system and let it run for a week.
The scientists were trying to see if the building blocks of life could create themselves from these simple ingredients. It's like asking my volunteers, if we give the magnets some energy, what are they capable of?
I'm just wondering, like, because we were doing this before with just one color, but if we took a bunch of them and threw them down together, I wonder what would happen.
How they tossed her just randomly.
Do you want to do it at the same time? And why don't you take some and we'll throw them all in the same spot?
Okay.
Why not?
I was interested to see if these things could actually assemble themselves without so much design from us. Could they actually, giving them that little spark, that little bit of energy, could they actually do this for themselves?
Okay, right, should we just chuck them in the middle?
Yeah.
3. 1, 2, 3.
Wow, that's actually quite impressive.
Cool though, look at all the diversity we have immediately.
With hardly putting in any.
With hardly, yeah.
We've got the start of the sort of spherical structure over here.
Yeah? Ooh,
That's not too bad.
That's a good one, isn't it?
And that was just by sort of random interaction of the things.
They've got like a little self-determination kind of thing going on.
Yeah, they self-assemble,
Yeah,
they sort of self-order themselves,
That's pretty
yeah.
cool. All acting in this way that's inescapable, do you know what I mean?
Nature works just the same way as the magnets. If the conditions are right, molecules can spring out of nowhere. That's just the way the world works at the atomic scale.
When we smushed everything together, it was really cool because actually lots of stuff that we couldn't have predicted happened. Really cool shapes that we didn't think being able to form, really complicated ones that we could pick up. We didn't know what was going to happen.
I was definitely surprised they would create all these different shapes the way they did, particularly some of the shapes, different colors fit together.
When you apply some energy, interesting things start to happen, as Stanley Miller discovered in 1953 with his remarkable experiment.
We and everything else are mostly composed of proteins, and proteins are composed of amino acids. Over the course of a week, he discovered that he had produced 5 amino acids just by providing a little bit of energy into this highly reduced, early Earth-like atmosphere. The most basic building blocks of life can appear sort of out of the blue, and it was a huge discovery.
To show this process in action, the team has a special machine that will give the magnets some energy. What will happen when they put the magnets in and turn it on?
Should we just turn it on?
Should we give it a go?
I've never seen a machine like that before. I had no idea what it was going to do.
It looked like a kind of giant egg tray with a surrounding wall.
Ah, there's another switch around here. And it's on.
Okay. Oh, here we go.
Given time and the constant input of energy, the magnets can form complex structures, all by themselves.
Oh wow, look, there's so much to fall already.
Wow. Oh, wow. Cool one.
Yeah, we got one.
And the magnets were bouncing up and down in the machine and started forming these balls on themselves. It was crazy.
I didn't know that they were going to form into balls. Like, that was a real surprise for me.
There were many throwdowns and bounces. We saw these very intricate structures coming together by themselves.
That's how atoms work. Over time, amino acids and many other complex molecules simply assemble themselves.
You can get, like, little things to form themselves. All you need is the right circumstance, the right force of energy, you know, the right surroundings, and they will do exactly what they're supposed to do.
Wow. That's crazy.
So far, my volunteers have worked out that life is a process in a biological machine, and how the elements of such machines can assemble themselves. But how did life begin? That's one of the greatest mysteries in science. Some researchers think that a particularly complex molecule assembled itself in pools of water and steam around volcanic springs. Others think it happened at the bottom of the ocean, near hot water vents. This particular molecule had a very special property. It could make copies of itself. These copies then made more copies, which made yet more copies, built out of the raw materials that surrounded them. That is what primitive life is. It makes more life out of stuff that is not alive.
Interesting.
To appreciate what this means for us, we need another experiment.
Wow.
Should we start getting suited up?
Yeah, let's do it. Yeah.
In this leg tent is all that is needed to make a primordial soup, a kind of ancient seawater.
Got salt, amino acids,
And all this water.
and a load of water.
We had amino acids, we had salt, we had a hell of a ton of water.
Should we start with the water?
Yeah.
The main ingredients are all found in nature, but none can be said to be alive. All they need to do is mix it together. They start by adding some water.
Let's have a look at what we've got here.
Amino acids.
Salt.
Do we want to?
Right, cool. Do you want me to do that when you start? Yeah, let's do this.
As we have seen, amino acids are the basis of all living things, and salt is what makes the soup like seawater.
Right, okay.
Yeah, changing.
What do we reckon now? Keep going with our.
I'd say.
Got this glycerol. Shall I?
Yeah?
Yeah, let's do it.
Get it in there.
Yeah.
All right.
Glycerol is a sugary alcohol, a source of energy.
Getting much thicker, right?
Yeah.
It might be hard to believe, but all that life needs to thrive is in this mix. A lifeless primordial soup, like the Earth's early oceans. So what happens if we introduce something that can copy itself? A few drops of this solution will change everything.
Oh God, which bacteria do you reckon it is? Here we go. I love that idea of a beginning. Do you know what I mean? And seeing where that beginning is going to go.
Bacteria. Our creation.
Now we have to leave the microscopic bacteria to do their thing for 24 hours.
I can't wait to see what it looks like.
Inside our soup, the machine of life has begun to whir. Each bacteria absorbs the water and amino acids, taking in the food source. Now something incredible happens. They begin to replicate. Every 30 minutes, each bacteria cell divides, so there are twice as many as there were before. 30 minutes later, there are twice as many again. Life is making more life using lifeless molecules. But how is this possible with such basic ingredients? The secret lies inside an incredible molecule, in the nucleus of living cells. DNA. Back in 1953, Francis Crick and James Watson discovered how it works. It contains the instructions for creating life.
The discovery of the structure of DNA in 1953 was revolutionary. They discovered that it was a two-stranded structure that was sort of a helix with a right turn. And so in that helix is all of the information required to build a particular organism. You can think of the DNA as the blueprints, and the builders, the things like proteins that are doing the job building tissues, building the organism. It all comes down to the DNA being the source of the hereditary material. It can copy itself and then transmit that information from one generation to the next.
The ability to copy DNA allows organisms to grow and repair themselves, and it's how all life forms reproduce. Just like the bacteria in our soup have been doing for the past 24 hours.
I had in my mind like primordial slime with like kind of, yellow floating on the top.
It was kind of like a spiral galaxy.
I was just gonna say, it almost looks like a galaxy.
It's tough to see tiny bacteria, but this grain has a special ability. It has evolved to produce green light when exposed to oxygen.
See kind of fluorescent bits as well.
In theory, that will let us see how much bacteria we have now. Let's see what happens if we blast it with oxygen.
Ooh.
Okay.
Even though the bacteria are tiny, together they can produce a light so we can see.
Very unexpectedly, we saw that the whole tank was actually glowing.
Wow. It turned into this amazing, I don't know, just this fluorescent sea.
The last thing I expected was for it to glow like that.
So I guess whatever we grew, the bacteria that we put in yesterday is producing all this light now.
How many drops did we put in?
3 or 4, didn't we?
We started with just a couple drops of the bacteria, and then the next thing you know, it is completely filling the environment.
I mean, think about how basic is water, salt, amino
And those
acids.
basic ingredients that we put in.
It's just amazing.
The rate and speed of this multiplication of life was absolutely astounding.
So how many bacteria do you think there are in our soup now?
I would really love to know how many bacteria are in it. I couldn't guess.
Gosh, about a million maybe? More. No, it has to be more. A billion.
In just 24 hours, a few drops of bacteria has become 66 gallons of them. Over 100 trillion individual cells. That's more cells than there are in a human being, such as the speed at which life can grow.
In 24 hours, that's happened.
Expanded to thousands of billions.
Once you have those building blocks of life there, it just explodes and it goes absolutely bananas.
This replication is the key to how we all came to be living on this planet. Because once it begins, almost anything can happen. Wherever we look, on the tiny or massive scale, life is endlessly varied, even though much of the internal machinery is the same. How did the machinery happen? And how did the organisms that use it come about? The answer is evolution. I've sent my volunteers back to nature. I'm hoping we can show evolution in action over just a few hours.
Well, this is odd. Trees, water. Intriguing. I had no idea what was going on walking into that tower and just seeing a tray and some water.
Okay.
Whoa, what's this?
I've asked Amanda and Zay to make 4 random shapes each, using a special molding material.
Wow, I've never seen stuff like this before. Let's go. Let's do this.
As it cools, it solidifies, so they don't have much time to make the shapes.
Oh God, it's getting really hard, really fast, isn't it?
It was fun playing with the liquid plastic and making the different shapes, just whatever came into our head. And of course, we didn't know what was happening.
Once they're happy with their shapes, they set the material in cold water. Now they're ready to make some more. To make sure they don't influence each other's designs, there is a dividing screen between Amanda and Zay.
My granddad would be proud of this.
Once they have completed their shapes, I've asked them to cover their ears and their eyes.
And we just had to wait and see what was coming next, and that was definitely quite thrilling.
This is where Sam gets to play his part.
I had these fantastic shapes, but I really had no idea what I was supposed to do with them. So we marched upstairs in the tower because it was the only other place to go. And I found that there was a fantastic catapult rigged upstairs.
It's like some kind of medieval trebuchet, onager type thing.
I saw that there was a target on the field downrange, nice red target to aim these shapes at. So the only logical thing seemed to be to launch these shapes from it.
Right, let's work out how this goes.
Flinging things off buildings is fun. But can Amanda and Zay make a projectile the right size and shape to hit this target without knowing what they are doing?
Let's give this a go. 3, 2, 1.
Although not designed for this purpose, the size and shape of some works much better than others.
Good roll, but it didn't get there in one go, so most of them weren't very fit for purpose. They kind of broke apart, flew off at funny angles, or just didn't really get very far towards the target.
Amanda and Zay are still blissfully unaware of what's happening to their handiwork.
3, 2, 1.
It doesn't matter if they bump, roll, or bounce. It's all about which gets closest. It looks like fun, but can you work out what it's got to do with evolution? These 4 shapes got closest to the target, and we'll go through to the second round.
Okay, ladies, we have another commission for you.
All right.
This time, they will each make a copy of the 4 winning shapes.
And I just thought, what's going on? Why do we have to remake the shapes again?
Okay.
Despite the fact they are trying to make identical shapes, small mistakes in the copying will change them ever so slightly.
It was really interesting doing replications of the same shape. Because using the same material and everything was slightly different outcome. You know, there are different sizes, different weights.
When you make one thing you're never going to make an exact replica of it. It can't be the same.
This is just like when nature copies itself. Small variations can happen in the process. Time to send our second round flying. Imagine each shape is a molecule that can copy itself, but only if it gets close to the target.
And fire.
Only the best shapes survive to reach the next generation. They are the best adapted to their environment.
3, 2, 1.
Amanda and Zay are playing the role of nature, introducing random variation in every new generation. There's one shape that seems to be doing best.
Trying to third generation projectiles. Starting to see a lot of similar ones. Seem a bit more fit for purpose. It kind of dawned on me what was going on in the kind of second, third iteration. Things started to look more cannonball projectile-like. Right, let's try first one. Safety out. 1, 2, 3. Wow, getting there.
With each generation, they get closer to the target.
5.
All the winners of this round look alike, and have all descended from the same original shape. There is a selection process at work, which makes the shape evolve. The shapes are perfecting their adaptation, without any conscious intervention from my volunteers. But how exactly does evolution work? This was explained by the genius Charles Darwin in his book On the Origin of Species.
The Origin of Species comes out in November 1859. It's the book that persuaded the scientific community that species might have come about by something other than independent creation by God. What Darwin tries to show you is that right under your nose, in nature, there exists a process which is powerful enough to produce new species from pre-existing species. And because there is never enough food to go around, because there are always too many predators, because there is competition, in that struggle for life, it will be those individuals who happen to be that little bit better adapted to their environments who will outsurvive their peers. They'll live long enough to reproduce and will pass the advantages that they were born with to their offspring. Over the long run, this process can persist to the point where one species has gradually morphed into a new species, and that's evolution.
It's time to let Amanda and Zay into our game.
Oh, cool. Is this a catapult?
Yeah.
I've never seen one in real life before.
So this is the amazing fun I've been having with your creations. You've been making my cannonballs.
No way.
What?
You're making my projectiles.
Fantastic.
You come and have a look over here.
Yeah.
And see what you're aiming to hit.
Oh, wow.
Okay, cool.
Yeah?
Yeah.
All right. Take up the chain.
Yep.
But don't pull it backwards. Just take
Okay.
it up. 3, 2, 1. Go!
So close.
Come on, we've got it.
So if only the four shapes closest to the target pass into the next generation, what do my volunteers make of all this?
For me, I'd say it was a metaphor for evolution.
3, 1.
It wasn't that we were designing this thing, it was designing itself.
Safety off.
Right, here we go.
3.
Ready? This is
This is the one. Come on, guys. This is the one. Sure.
Let's go see.
Oh, there's one!
There's
A couple of the misses.
Nearly! Nearly!
We did it. Just about.
Yeah! Yes!
That's a good core of an inch shoulder. I didn't think that this could happen so fast, that we could produce something that could hit the target so fast.
Life perfects the imperfections each time. And then I guess over a really long period of time, that's how we've come about.
Without any intentional design, in a matter of hours, random shapes have evolved. But complex life needs one more ingredient. We have worked out that we are biological machines, and that we have been created through a process called evolution. But this process takes time. An incredible amount of time. It's hard to really appreciate just how old the Earth and life is. Let's see if we can fix that with some harmless fireworks.
It was just like, whoa! It just absolutely scared me. I was going to go down to the ground.
Top, drop, and roll.
Oh my God.
Imagine that firework represents 250,000 years. Longer than the age of our species. They are laid on a trail stretching back in time. If 4 flashes happen in 1 second, that makes 1 million years. How long would they need to follow the flashes for to get back to the beginning of life on Earth?
I think it'll run for about 30 seconds to a minute, 30 seconds.
1 minute and 28 seconds. I think that it would probably run for about 4.5 minutes. I love running.
How close do you think they'll be? After just 6 seconds, we are back to the time when the first ape-like creatures walking on 2 legs appeared. About a minute later, they are entering the age of the dinosaurs.
We've already gone for a minute, which is more than my initial estimate. So I'm wondering how long we're going to be running for, and if I should have bought some more appropriate shoes, essentially.
Dinosaurs walked the Earth for almost 1,000 times longer than we humans. So that's 1,000 flashes, taking a further 4 minutes.
It's crazy to think that each one of those flashes is more than human history.
We're at even a tiny part of the time since the dinosaurs died off, which is ridiculous.
After 7 minutes 30 seconds, we are back to when the first creatures began colonizing dry land. After 9 minutes of running, we are 540 million years in the past, when the earliest complex life started appearing in the oceans. But how do we know all this? The team can take a breather. The first step to understanding this was taken in the 18th century by a Scottish farmer named James Hutton.
Going back 250 years, the accepted thinking at that time was that the Earth was young. And when I say young, I mean just a few thousand years. James Hutton was a fascinating man. He started off studying chemistry and medicine before spending many years farming in the Scottish borders. And it was really his time as a farmer that brought him close to the landscape and to the rocks. Hutton came up with the idea of cycles in geology. He saw erosion taking place, he saw sediments being washed off the land surface into the oceans. And other people had noticed that before, but then what Hutton realised is that whereas old rocks were being worn away, new rocks were being formed. And new rocks would then be uplifted, and the whole cycle would begin again. And here at Siccar Point, he famously found this, which is a geological unconformity. Is a break in time. Essentially, these underlying rocks would have been at one time formed horizontally and tilted up almost vertically and eroded. And that took time, that period of mountain building and erosion. And then at a later date, you had these horizontal rocks laid down on top. The break in time that you needed for these rocks to then have been formed in this configuration, Hutton knew it had to be much longer than a few thousand years. It had to be many millions of years. Earth simply had to be much, much older than anyone had previously thought. James Hutton opened up the vastness of geological time. He gave us this true sense of time. And that, for me, it just makes James Hutton a standout hero.
James Hutton's work allowed scientists to build up a picture of the order in which life evolved. The remains of organisms that lived during a period are found preserved as fossils inside layers of rock. These layers helped scientists date each of these marvelous creatures. Now can the team finally understand how old life itself actually is? In the quest to grasp the age of life, my volunteers are still traveling back in time. After 35 minutes, they are 2,100 million years in the past, with the first multicellular creatures.
We were running at some points and we couldn't actually see the end of it. It was just going on and we were going around corners and it was going and going and going. It just seemed like it was endless.
But there's still a long way to go. My volunteers have now reached the era in which only single-celled organisms existed on Earth. The final bang and the beginning of life around 4 billion years ago.
Finally made it to the end. Well done, guys.
Awesome. It was a really good way to appreciate how long life has been around for.
It's a number in years that is so much more than numbers that we deal with on an everyday basis. It's very difficult to grasp.
It's just crazy to me because that shows how much time really has passed since the beginning of life.
My volunteers ran past 16,000 flashes to get back to the beginning of life. Through the age of the dinosaurs, to when creatures first lived on dry land. Past the first complex sea creatures, to simple multi-celled organisms. Through 1,000 million years, where the only forms of life to be found consisted of just a single cell. What a journey.
So much has come before us, and we are such a small, insignificant part of the history of the world.
We've basically come along right at the end of the party. We're kind of the ones who don't know how to behave and gets everyone else thrown out.
We're just a flash. I was thinking that we were actually the babies of the universe, but it's not even that. We're actually like the glint in the milkman's eye of the universe.
So what are we? We began deep in the distant past, as the building blocks of life created themselves. Then billions of years ago, a molecule with a remarkable ability began to make copies of itself, from the raw materials of the planet. A chain reaction had begun, and evolution took over. So here we are, complex biological machines, capable not just of replicating and passing on the chain reaction of life, but also figuring out how we got here.
It's amazing to think that this huge chain reaction has been going on in the world in terms of the creation of life, and we are the last in the line.
I find it makes it absolutely amazing because everything that's involved in this constant process it just makes the fact that I'm here sitting in this environment on this rock that made this material incredible and wonderful.
That aha moment and just understanding the reality of what's going on around you, it's euphoric. That sort of defines us in a way as a species, that we can ask these questions and we want to find out what the answers are.
I'm going to start looking at just the smallest things differently. So if I look at a flower on a walk in the park, I'm going to think of those flowers as being part of this process too. We're all part of this world. They've been created over these billions of years.
The original primitive life has been running ever since it first began, and is now only just passing through you. So that is what we are. Part of a single ancient process, clambering about on our tiny ball of rock as it orbits the sun, passing the chain reaction on and on. We are all already billions of years old, which makes us pretty special. Where are we? That is part of what it means to be human.
Where did we come from? Oh no!
My name is Stepphen Hawking, and I believe that anyone can answer big questions for themselves. So with the help of 3 ordinary people and a team of experts,
we have come to understand our origins, and this is new.
We are going on the ultimate voyage.
Wow, that's impressive.
A quest to answer the greatest mysteries of the universe, using the power of the human mind.
Wow! It must have been so exciting to see that for the very first time.
Because anyone can think like a genius.
Genius by Stepphen Hawking was made possible in part by contributions to your PBS station from viewers like you. Thank you.
What are we?
Have you ever wondered what you really are? Have you ever stopped to think how you got here? A complex biological creature living on a ball of rock spinning through space. If so, you are in good company. What are we is a question that has been asked for thousands of years, contemplated by some of the greatest minds who ever lived. But even today, far too few people know the answer. So let's see if we can put that right. I have asked 3 curious minds to join me on a journey of discovery. A series of fun challenges awaits them. They will be given tools and equipment. Can they follow the greatest thinkers in history and grasp what we really are? The first step to finding out is to ask, what is life itself?
What is life? That's a difficult question to answer.
What is life? This kind of seems like a very simple question.
Something which is able to, which is born and can reproduce itself.
Receiving energy, giving energy.
Reproducing and reacting to the world around you.
That's a really tricky question to answer.
This machine illustrates the first key principle behind what you are. It has lots of moving parts that trigger each other in a chain reaction. It's designed to reveal something that you may find disturbing. Will my volunteers get the point of the machine?
Interesting.
Yeah. Okay.
First, they had to find out how to start it.
I wonder what happens over here, though. Look at this arm. Is that supposed to be like a god thing, you know, because it's an arm out of the clouds or whatever?
I think you're probably right. It's beginning up there. Should we give it a go and see if it'll work?
Yeah, that's what's going on over there.
I think it starts up here, right? Give me a countdown, guys.
Okay, 5, 4, 3, 2, 1. Okay.
on the top of this. Yes. Keep going.
Nice.
Okay.
I love that.
Oh, I think it's got stuck.
The machine works by transferring an impulse from one place to another, sustained by the input of energy. There are lots of different moving parts, each following the laws of physics, and together they keep the impulse moving.
Is it going to be enough? Yeah.
Stepphen Hawking's machine of life.
Ooh.
So what has this got to do with us?
What do you think? Reset it in order?
Let's try and reset it, and maybe they'll help us figure out. One thing always leads to another. So one process has to happen before another process happens. Like certain circumstances have to occur before something can move forward.
It helped to show me that everything has a cause and effect. It reminded me all about chain reactions.
So I guess we get cause and effect, and everything has to build up and up and up.
Should we give it a go?
Let's give it a go.
I think it might have broken.
No,
It's spinning up. Whoa.
Oh, go on. Nice. Did we reset it correctly?
It was a really powerful demonstration of how all those processes work together.
Oh, yes.
You've got all these different things that create one result.
It's gone premature.
That's okay, that's okay.
My machine is actually a very simple version of what is going on inside your body. This is what you look like on a microscopic scale, and it really is quite incredible. Where my machine features dominoes and pool balls, your body has molecules, chains of atoms of carbon, oxygen, hydrogen, and other elements. You are made of billions of tiny machines, all triggering each other. You are a giant chain reaction machine. Discovering this has taken centuries of work by scientists. It all began by looking at a drop of water.
People had always assumed that what they could see with their own eyes was the limit of the physical world. But all that absolutely fundamentally changed in the middle of the 17th century, when a Dutchman called Anthony van Leeuwenhoek made one of the greatest scientific discoveries of all time, and yet he himself was a cloth merchant, a draper. It was his interest in microscopy, microscopes, that he was using to examine the quality of cloth, that he then, with his innate curiosity, kind of applied to the world around him, that literally opened up a whole new world of science. This is a replica of his own handmade microscope. And this, believe it or not, it might not look like very much, but this was the most powerful microscope around at that time. Sandwiched between these two sheets of metal is a tiny glass sphere. And whatever you had attached to this spike here, you could see magnified just over 200 times. He took a droplet of water, and when you held it up to your eye, like this, he saw what no one had ever imagined. This whole new world. The water droplet was literally teeming with life. He described them as little animals. To us, we now know that they are microorganisms. It must have been so exciting to see that for the very first time. He looked at all sorts of things using his microscopes. He looked at himself. He looked at skin, and he looked at blood. We are all fundamentally made of similar things.
The idea that we might be made up of invisibly tiny components was something of a shock. After all, nobody likes to think of themselves as a machine. not in me. But let's go back to the contraption, because it has another feature. It can be made to run round and round in a loop. To do that, we need one more part. This rather attractive plastic figure joins the end of the machine back to the beginning. Now the challenge is to keep it going.
We would have to put in enough energy and be quick enough to reset the pieces before they came round again.
Make it run in a loop? I can try. That's what I can do.
Making a chain reaction machine run in a loop should help the team understand what we are.
If we get 5 cycles, I'll buy the drinks.
Yes!
Okay, let's do this.
3, 3, 3, 2, 2, 2, 1, 1, 1, go!
Excuse me.